Okay, so what you're going to be working with today is vapor pressure. And this is one of the things that I really think is a good ACT score builder. How many of you have seen a vapor pressure diagram before? Okay, where'd you see it? In this class or someplace else? On the ACT? Yeah, okay. So if you recall, yesterday, when we last left our chemistry heroes, we talked a little bit about equilibrium vapor pressure, and we said that it was the pressure exerted at a given temperature by a vapor that's in equilibrium with its liquid state. So we have our little sealed system, we have our liquid, and we have our vapor. And they have to be in equilibrium, which means the rate of opposing change is the same. So for every molecule that leaves the liquid phase and enters vapor, one leaves vapor and enters liquid. Yes? Remember? Okay, good. Now, what I wanted to know, what I asked you as sort of a challenge question is, what do you suppose happens when the equilibrium vapor pressure equals the atmospheric pressure? What do you suppose happens at that point? What happens when the pressure that vapor is exerting is the same as the atmospheric pressure? When the pressure that vapor is exerting is identical to atmospheric, there is nothing that holds any of those particles in the liquid phase. What does that mean? It means it boils. So when you hit the temperature where the equilibrium vapor pressure is equal to atmospheric pressure, the stuff boils. The vapor that is inside the water column, so remember we said that boiling was different from evaporation because in boiling the bubbles actually start down in the water column because the pressure that the vapor is exerting on the liquid is the same as atmospheric. So all of the particles in here are suddenly able to escape to vapor phase. What that means is that we can use a vapor pressure diagram to determine the boiling point of a liquid. So I'd like you to look at line number 4, which is water. These were color-coded in my original, but they're not anymore because I don't have that capacity. And actually I should make this a chart. And then we can see this more clearly. So we've got, on the page that you have, we have a line that indicates that this is normal atmospheric, so 760 torr. And then we have a range of temperatures on the bottom. And if you look at the temperature 100 Celsius, you will find a line for water, and that line for water crosses 760 at, well, gee whiz, 100 Celsius. What's the boiling point of water at normal atmospheric pressure? Don't all jump up at once. What's the boiling point of water? 100 Celsius. So if we have some substance, any imaginary substance or whatever, whose vapor pressure line looks like that, we can find the boiling point of that substance by looking at where that vapor pressure line crosses the atmospheric pressure. So if this is 250 Celsius, this substance would have a normal boiling point of 250 Celsius. Okay, that's fairly easy. That's pretty intuitive once you get that. You're like, oh, okay. So wherever the line crosses normal atmospheric, that temperature is the boiling point. I can read a diagram. This is good. Here's where it gets a little bit more challenging. Let me get rid of these guys. So what if I were to ask you, Well, what if I were to tell you, so that's 760, here's, let's call this one 800 torr. So in Death Valley, which is actually below sea level, or in a submarine, you know, below the surface of the ocean, where you have higher than normal atmospheric pressures, at 800 torr, would the boiling point of water be higher or lower than 100 degrees? Point. Yeah, it's higher. Yeah, at higher pressure, you're going to have higher boiling points. So what if we are in a situation where we have reduced pressure? What's that going to do to boiling point? Lower it or raise it? It's going to lower it. One of the questions you have on your worksheet talks about at elevation. Have you ever read the back of a box of cake mix? Have you noticed that there are high altitude baking directions? Has anybody seen that on a box of cake mix? Okay. I lived at high elevation. When I lived out west, I worked in a bakery of all things, bakery and cafe, and we were 8,000 feet above sea level. So to make brownies, we had to add extra flour. There was something else we had to do to the recipe. I think we had to lower the temperature and extend the time. So you added like a quarter cup of flour for every so many cups of mix, and you lowered the temperature, you know, however many degrees for every 1,000 feet of elevation above 5, and you extended the baking time. You know, there was a whole formula for doing this. Why would the baking times and temperatures change at elevation? Let's draw some imaginary lines here. So let's say we're down this far in atmospheric pressure. Is the boiling point of water higher or lower?
Lower.
It's lower. Which means if you're baking your brownies at 350, the water's going to boil off and be gone sooner. And there are all kinds of other chemical processes that happen when you're baking, like gluten development and things like that. You need enough time for those other chemical reactions to occur completely. You need time for the leavening to work. So you lower the temperature and you extend the time. There are all kinds of compensators, all because the boiling point of water changes. Mountaineers, people who are backpacking or hiking up at very high elevations, people who are, you know, living in the Himalayas, where they're up at very high elevations, or the base camps on Everest, like the ones that just got hit in the earthquakes and avalanches that followed. There's a whole complicated formula because, of course, you're depending on using fuel to melt snow and boil water for food. Well, your water boils at a lower temperature. Now, your fuel is also a pressurized gas, so you know the temperature at which that's going to burn changes a little bit. But for the most part, you actually can get away with, I believe it's a little bit less fuel at high elevations because your water boils at a lower temperature. And so you're not using as much fuel to get it there. Okay, now, can you manipulate pressure? Whoops. Can you manipulate pressure in order to manipulate boiling point? Yes, you can. So you can do that in two different ways. There are two ways in which you can manipulate pressure in order to manipulate boiling point. One is you can reduce pressure to get a liquid to boil at a lower temperature, and that's done through the use of a vacuum chamber. You can actually pump out atmosphere from a chamber. And we've got a vacuum pump in the back. Hopefully we'll get to use it before it goes to wherever it's going. The other thing you can do, you can intentionally raise the pressure on something to get it to a higher temperature. Why would you do that? Why would you intentionally raise the pressure on something to get it to a higher temperature? What's the premise behind pressure canning? So some of you have seen a pressure canner, and it's basically a large vessel with a locking lid. That's really important from a safety perspective. And that lid has a gasket. And there are two different kinds. One has a pressure dial, one has a pressure weight. there are different kinds. And these are big pots. I should bring mine in, but no, that's too much of a hassle. And you set your jars in there with your food in them and your lids on them. And you lock that lid down. And it's a very serious lock. Like, you cannot remove the lid when the vessel's under pressure. And then you heat it. And you've got water in here. The jars are about half covered with water. What happens? Nothing happens? We'll play stand-up lottery. Okay, so talking about pressure canners and the fact that a system under pressure raises the boiling point of water, and that allows us to heat everything to a temperature sufficient to kill germs. There we have our good old canning jar, and there we have a pressure canner with a dial gauge. We have some mysterious substance here with a vapor pressure line, and the marks, the tick marks on that graph are not, they don't give you a high level of precision. So each one of these spaces is 50, and this is degrees Celsius, this is torr. So every one of those spaces gives you 50 degrees Celsius to play with. Every one of the spaces up the y-axis gives you 100 torr. So how do you get the best possible reading? So let's say we want a reading, I'm going to change the color of this line, at, where's the worst example I can possibly think of? Here. Let's say we want a reading right there. Well, if we look at where this line intersects, and that's our mark, this is 300, this is 350. You could say, oh, I don't know, maybe it's like 345. It's really close, 349. What I'm going to tell you is anytime you're faced with a graph like this, and you'll see these on the ACT, what you need to do is look at how much of this space is how many whatever gradations. So if that's 50, if, oh, and I just did all mine wrong, yeah. If that's a full 50 degrees, then half of that is 25 degrees. You visually are really, hate to tell you this, all of us, you're really only good for estimating about half of something. We're lousy at visually estimating anything other than half, but for the most part, humans are pretty good at visually cutting things in half. So if you can cut that in half, and then cut this space in half, and that's not quite in half, we can say, oh, okay, that's about a quarter of that distance. So that would be, this would be 25, half of that would be what? 12.5. So we could take 350 minus 12.5, we get 338, 337.5, okay. Can we say 337.5 based on the level of precision we have in that graph? No. But we can round that, and we could probably say with about as close as we can get would be to say 340 degrees Celsius. Okay. Now you will see some graphs on the ACT, and I've got one that comes up someplace, and I can't remember where, that have variable scales. So the marks between here, it's very often a logarithmic scale, and here aren't the same. Oh, we see it on the pressure graphs. We see it on the pressure graphs. So this might be 1, and this might be 10, and this might be 100. Oh. So you have to be really careful in looking at what the scale is telling you and dividing those distances. So if this is 1 and this is 10, now is it perfect? No, it's not. But you can say, okay, well, this has got to be approximately 5. You know, you can do that division of distance between the scale marks that they give you. So if we look at, and I'm just faking this, if we look at the line for bromine, it is crossing, there's the half mark. It's crossing, and actually on your chart, it crosses a little bit below the next half mark. So we could say, well, this is 100, this is 50. We can estimate this to be 75. Half of the distance between 50 and 75. Well, 12.5 plus 50, 62.5. Okay, we can't be that precise. We basically have one sig fig to go with, which means we should probably call it 60. So you see how sig figs play into your certainty on this also? So the next one, at 800 feet above sea level, atmospheric pressure is 550 torr. At what elevation? At that elevation, what's the boiling point of water? Give me one answer. Tarek.
90.
90. Who has 90? Okay, give me another answer. Justin. 8? 80. Okay. If we look at the 550 torr line. Oh, wait, I may have screwed this up. At that elevation, what is the boiling point of water? They are a little tough to see. Okay, so 550.
I'd say 87.
Um, 90 is a good bet. 90 is a good bet. If you look at it and it's halfway between, you say, ooh, 87.5. Then that's 90, because you don't have that many sig figs to work with. You can't say, it is 92.73. Yes, ma'am. If we go back to the concept of sig figs, if you look at that graph, how many sig figs do you have to work with between 50 and 100? 1. So your answer should reflect that. Now, I don't know if the ACT, if the people who write the ACT do anything good with sig figs. I know the publishers of our physics book do terrible things with sig figs. Their sig figs are constantly wrong. It makes me crazy. But, realistically, if we're looking at it and we're thinking about how much certainty do we have, we don't have enough certainty to say, 85. Now, realistically, would I mark 85 wrong? I might take off 1 point out of some number of points. I probably would mark it wrong, because it's closer to a true answer than something else. Okay, if a pressure canner, back to pressure canning, I like canning. If a pressure canner is able to place its contents under 1,000 torr of pressure, how much is the boiling point of water elevated? So, give me an answer. Alicia. 10 degrees. Who else has 10 degrees? Awesome. Yeah, it's gonna go up about 10 degrees. And again, it's halfway between the halfway, so that would be, 12.5, but we don't have that level of certainty. Now, as we get up into the 250s, the 150s, well, we still don't have that level of certainty, because we've always got our 100 or our 200 on the other end of that. Okay, to what extent would you need to lower pressure to boil water at 50 degrees Celsius? Who's got an answer? Alexis. 660 torr? Who's got 660 torr? Okay, who's got another answer? What's your answer?
105 torr.
Okay, who's got 105 torr? Let's do that with sig figs. Who has 100 torr? Okay. Oh, okay. You were saying you would have to lower it by, okay, to what extent? Okay, then yes, you're right. So you would have to lower it 660 torr to get it down, because you would need an atmospheric pressure of about 100 torr to get water to boil at that temperature. Okay, yes ma'am. Okay, so under normal atmospheric conditions, what temperature is required to vaporize mercury? Give me an answer. Adam? 350? Who's got 350? Okay. Who's got a different answer? James? 355. Okay. 355. Who else has 355? Okay. Who's got another answer? Bryce? 360. Who's got 360? I do. So yeah, I would say 360 is probably a better answer, because if you look at that again, it's about halfway up the halfway. So that would be your lower value plus 12.5. Well, we can't really do 12.5, so, but we can do 10. Okay. Number 6 and 7. These are distillation problems. And I don't know if there were any problems on the ACT that referenced distillation. We don't get to do distillations in here. I would love to someday. What is distillation? Who knows? You've seen distilled water. What is distillation?
Removing alcohol from water.
That's one
Or
form.
another solution.
Okay. Do you have a more complete answer? Okay, let's go with the broadest definition. Separating two substances, typically based on their boiling points. It is most commonly used with water. It is most commonly used to remove impurities from water, or to remove alcohol from water. It's actually to remove the water from the alcohol in the case of the kind of distillation you're thinking of. Because while you boil, so how does a distillation process work? Let's look at it. I'll show you this first. So here we have a combination of water and we'll say it's ethanol. Okay. We heat that to boiling, and then we cool the vapor until the vapor recondenses down into another container. So whatever in this mixture has the lower boiling point is going to boil first. It's all going to be vaporized, and when it travels through all this and it recondenses, what you end up with up here is pure whatever substance A was that had the lower boiling point. Okay? So in the case of water and ethanol, which one has the lower normal boiling point? Ethanol. So you boil off the ethanol, you recondense the ethanol here, now you have pure ethanol, or as close to it as you can get, and here you have, when you're done, pure water. That's the goal. Okay, so if you have a setup like this, you need to control the temperature closely. Why? Yeah, you don't want to vaporize the water and then end up with a mixture over here. You've just defeated the whole purpose. So you have to control the temperature here. If you are doing a steam distillation of water and ethanol, you need a vapor pressure chart like this, because you have to understand what temperature you need to take the mixture to get all of the ethanol to vaporize and to not have one molecule of water vaporize. So, what temperature would that be? Who's got an answer? Give me an answer.
76 degrees Celsius.
Number 6. 75. Okay, who has 75? Okay, who's got a different answer? What do you have, James?
80.
80? Who's got 80? Who's got a different answer? Okay. 70? Who's got 70? Okay. All right. This is one where there is a range of correct answers. The key is, what do you not want to get it too close to? You want to have a good buffer from 100. Okay? The answer I have down is 90. So the boiling point of ethanol, what do you see is the boiling point of ethanol here? Roughly 75 degrees Celsius. Okay? Ethanol boils off vaporizes at roughly 75 degrees Celsius. You want to make sure you're above 75. So 80 is a good answer. 90 is a reasonable answer. 75 probably isn't a great answer. Because if there's any uncertainty in your process, you may leave ethanol behind, and you don't want to do that. So you want to make sure you're getting it well above that 75, so you make sure you vaporize all the particles of ethanol. 80 is a great answer. I did 90 because it's a little bit of insurance. It gets you a little bit further. But yet you shouldn't start to vaporize a single water molecule at that temperature. Okay, same question. If you have a mixture of ethanol and diethyl ether, where do you want to take it to make sure that you get all of the diethyl ether, or diether ether, and none of the ethanol. So who's got an answer? Okay, Hannah. 35 to 60. That's a heck of a range. Okay, who has 35? You have 35. Who has, we'll just go up by fives. Who has 45? Or that's tens, huh? Who has 55? Who has 65? Okay, we'll just do other answers. Tell you what, I have 50. Who's got 50? Okay. Now the nice thing about the diether ether and the ethanol, there's a pretty good range. There's a pretty good gap between their boiling points. So you've got enough room to give yourself a little bit of a buffer, and you should be able to get the diether ether to vaporize far enough before the ethanol that you don't run the risk of vaporizing ethanol. Okay, at 500 torr and 75 Celsius, which of the substances on the chart would still be in a liquid phase? Anybody, James?
Water and octane.
Mm-hmm.
Ethylene glycol.
Ethylene glycol.
And mercury.
And mercury. Yep. Water and octane, ethylene glycol, and mercury. Those would all still be in a liquid phase under those conditions of pressure and temperature. Questions, comments, or concerns on this? Okay, so this slide basically covers all the conversations we've had this morning. And it happens when the EVP of the liquid is equal to atmospheric, and we talked a little bit about what happens with pressure or elevational changes. The molar heat of vaporization is we're not going to do any of the math associated with this. Depending on the internal forces of attraction in a liquid, you get a different amount of energy that's required to vaporize things. So here's another kind of question I could see happening on something like the ACT or on my test. Given the choice of 3 of these substances, so ethanol, N-octane, and mercury, which would you expect to have the highest molar heat of vaporization? Well, you have to know what molar heat of vaporization is. It's the amount of energy required to vaporize 1 mole of a substance. The lower something's boiling point, the lower or higher its molar heat of vaporization. What do you think?
Mercury.
The lower something's boiling point, the lower or higher its molar heat of vaporization. The lower, yeah. The lower the boiling point, the less energy it takes to vaporize a mole of that substance. So yes, of those 3 named, which one would you expect to have the highest molar heat of vaporization? Mercury. It's the one that's going to cling on to liquid form the longest. It takes the most energy to convert it all. Anything that's got a high molar heat of vaporization makes a good cooling agent. Water is the classic example here. It takes a lot of energy to vaporize a mole of water relative to other things with similar atomic masses, similar structures, because water's got those 2 forms of intermolecular forces of attraction. So it's got hydrogen bonding, and it's also got the fact that it's a polar molecule. So water really likes other water. Well, remember, we keep saying water only likes 2 things in the universe: itself, everything else. Because of that fact, it takes more energy than you would otherwise expect to vaporize water. So water's a great cooling agent. Look at this chart again. Who here knows where you could find ethylene glycol in your house? Okay, I have 1 candidate. Anybody else think they know where they could find ethylene glycol? In your home surroundings, where do you think you could find it?
In your car coolant system.
Yes, ethylene glycol is antifreeze. Okay? Look at the boiling point of ethylene glycol versus the boiling point of water. Why do we use a mixture of water and ethylene glycol as a coolant? It takes more energy to vaporize ethylene glycol, so that means it offers better cooling protection than plain water. So if you have a leaky radiator and you're putting plain water in it, you're reducing the amount of protection that your engine is getting from overheating. For any substance, I mean, this is one of the ways to identify or characterize a substance, is to see how much energy it takes to vaporize it, to basically test for its molar heat of vaporization, because for every substance known, there is a characteristic molar heat of vaporization. So this is where we're going to talk a little bit about solidification, also known as freezing. So we did that little triangle yesterday of all the phase changes, and we at that point we're just really talking about the phase changes from liquids to solids and liquids to gases. Here's where we go from a solid to a liquid or a liquid to a solid. And the same thing that we saw with liquids and vapors, where there's a heat relationship. Okay, I'll tell you a little story. I love story time. So when I was a kid, there were still some pretty big strawberry fields in Columbiana County, northern Columbiana County. And the farm next door to my grandparents' farm had an entire front patch. It was probably about 5 acres of strawberries, but that's a lot of strawberries. And I remember on cold nights in the spring, like those real cold nights we sometimes get in May, when the strawberries are already, they've got blossoms on them, and they're going to set fruit, but they haven't set fruit yet, or maybe they've got very small fruit. And Burdell, that was the neighbor, on some of those real cold nights, would get out the irrigation systems, and he'd start pumping water out of the pond. And he would saturate the strawberry field, like soak it. There would be water dripping off of everything. And I remember as a kid saying to my dad, why is he doing that? To save the strawberries. We're going to have a frost tonight. So, what the heck was he doing? It has to do with this relationship right here. So, if you remember this chart that I drew the other day, solid, badly, liquid, terribly, gas. We're not going to make water plasma out in the fields anytime soon. If this is kinetic energy, okay, increasing kinetic energy, when a substance goes from a solid to a liquid, what happens? Where does that energy go? Into the substance or out of the substance? So when something makes this transition, when it melts, when it liquefies, does the energy get absorbed by the substance or released into the environment?
Absorbed.
It gets absorbed by the substance, because this substance goes from having this much energy to having this much energy. When a substance goes from being, we'll do another color, a liquid to a vapor, liquid to a gas, where does that energy go? Gets absorbed into the substance, because the substance goes from having this much energy to having that much energy. Well, now let's think about this in reverse. If that same substance goes from being a gas to a liquid, it condenses. Where does that energy go? Where? Out into the environment. It just dissipates. So that substance gives off some amount of heat energy as it condenses. If a substance goes from being a liquid, such as water, to a solid, such as ice, where does that energy go? Into the environment. If your strawberry plants are completely saturated, covered in water, soaking, dripping, when that water freezes, what happens? It heats up the plants. The energy that that liquid water gives up as it converts to a solid is transferred into the plant. So in the morning, you see plants that are covered in sheets of ice, but the actual plant tissue is unharmed. And there are fantastic pictures. Every year there will be 1 or 2 times when the orange crop in Florida, they do get freezes in Florida every now and then, and you always see pictures of these orange trees just dripping with icicles. They do the same thing there. They hose the heck out of the orchards. They soak the plants. And then the energy that's given off by the water as it solidifies actually protects the plant. So it's a practical use of this knowledge. But it's the same relationship we saw in a vapor-liquid system. The solid plus some amount of heat gives you a liquid. Those solid particles have to give up heat to become a liquid. And in equilibrium, that ends up being absorbed again by liquid particles that are, or or I'm sorry, solid plus heat. The solid has to absorb heat to become a liquid. Heat is given off by liquid particles which are re-entering the solid phase. So we have this same, a glass of ice water has the same relationship if it's at equilibrium, where particles are liquefying and freezing continually. And if it's at equilibrium, the rate is the same. If the ice in your cup is melting and it's slowly all going into liquid phase, it's not at equilibrium, because the change is only running one direction. So that's a system at equilibrium. As you might have guessed, there is a corollary to the molar heat of vaporization, which is molar heat of fusion. How much energy... Now, we talk about molar heat of fusion sort of in the reverse direction, because it's how much energy is required to take 1 mole of a substance from solid to liquid. It always sounds to me, I always get confused because it sounds like molar heat of fusion should be how much energy is given off when it fuses into a solid, but it's not. So it's just backwards. And it's just like molar heat of vaporization in that the stronger the forces of attraction, the larger the molar heat of fusion. So the stronger those forces of attraction, the more it wants to stay as a solid and not become a liquid. And I got emails from some of you. Of course, the offer is now null and void. These are the other two that we hadn't talked about yet, sublimation, deposition. Most of you are familiar with sublimation. If you leave an ice cube tray open in the freezer for a very long time, the ice cubes seem to magically disappear. They're just they're subliming. They are sublimating. If you hang laundry on the clothesline in the depths of winter, your clothes will eventually dry. It will just take longer, and it's all thanks to sublimation, because the water in that fabric will freeze, and then from a frozen condition, it will slowly sublimate, but it's a slower process than evaporation. These two really mostly occur at very low temperature and pressure, so they're not things we see very commonly. I want to end there because we're going to start off with phase change diagrams tomorrow after your FIP quiz. So you'll do your FIP quiz, it won't take you long, and then we're going to do some phase change stuff, and I'm going to give you a practice sheet on phase change diagrams because I think these are really important for the ACT. How many of you remember seeing a diagram like this on the ACT? Yeah. The science ACT typically it's going to have either a vapor pressure diagram or a phase change diagram, and there are a couple other things we see. I think there's some kinematics diagrams often, but these are helpful. So we'll start that tomorrow.